All right, a company that rents DVDs from vending machines in a grocery store has developed the following probability distribution for the random variable x, which is the number of DVDs a customer rents per visit to a machine, and we need to make a probability histogram. So when we're doing a probability histogram, our x-axis are the values that can happen. Now, 0 isn't possible here, but unless we want to show a break, I'm just going to include 0. I might move those a little bit closer. So those are the values our variable can take, and then on the side we would want probability. And I could go all the way up to 1.0, but I don't need to. I only really need to go as high as my largest value, and that's 0.5. And so on my y-axis, this is really p of x, and on my x-axis is the number of DVDs. And then we just draw our bars. So my bar for 1 should go up to 0.5. My bar for 2 should go to 0.3. And then my last two bars should be at 0.1. And there's our probability histogram. All right, for part B, we are supposed to find and interpret the mean, or the expected value. My variable is x, so my symbol for the mean would be a mu with an x. You could show the work. You can also just show the formula, which is sigma xi pi. And then if you put your x values in list 1 and your probabilities in list 2 and run one var stats, making sure to put list 1 and list 2 together in your lists, then we get our value, which would be 1.8. And then we need to interpret it as well. So in this case, it would mean we would start with over the course of many visits, we would expect customers to rent 1.8 DVDs from the machine on average per visit. And that interpretation hits all of my key things. We're talking about over the course of many visits, we would expect customers to rent the 1.8 DVDs from the machine on average per visit. And then we have our context as the machine and the visits. For C, we need to find and interpret the standard deviation of x. So first, the formula we need is mostly on our formula sheet. Now the catch is, the one on your formula sheet looks like this. But that is for variance. On your formula sheet, there's a squared with the sigma, which tells you it's variance. Since we want standard deviation, we need to just put a square root over the whole thing. And the value, when you run one of our stats in your calculator, we get it at the same time we get the mean, would be 0.98. And then for our interpretation, on average, for each visit, the number of DVDs differs from the mean by 0.98. Next, we are asked to describe p x greater than or equal to 2 in words and in context and find its value. So this means the probability that a customer rents 2 or more DVDs on their visit to the machine. And then to find the value, if we want greater than or equal to 2, we just need to add up the decimals for 2 or higher, which in this case would be 0.5 when you total them up. And then part E, suppose the profit the company makes on each customer's visit is 75 cents per DVD minus 5 cents in fixed costs. That is, if P equals profit, then P equals 0.75x minus 0.05. Use your results in B and C to find the mean and standard deviation for P. So first of all, we need to refer back and get our mean and our standard deviation from the earlier questions. The mean was 1.8 and the standard deviation was 0.98. And now we want to find mu of 0.75x minus 0.05. And you could actually use just the new subscript of p, and that would be fine. They've already defined that to be this. That would be totally fine. And in general, you've heard me say a bunch now, the mean is nice. So I want to take 0.75 times my old mean, and then subtract our constant of 5. So we are, in this problem, we are multiplying by a constant of 0.75, and we are subtracting a constant of 0.05. So my new mean would be 1.3. My new standard deviation for this variable, we need to be a little bit more careful. When you have a standard deviation, when we multiply by a constant, the standard deviation gets multiplied, so we are going to take 0.75 times 0.98. But when we are subtracting a constant, that does not impact the standard deviation or any measures of spread. So that's all we are going to do here to get a new standard deviation of 0.735. Number 2, a game that costs $10 to play has you spin a wheel numbered 1 to 10, where each number has the same chance of happening. If you spin a 1, you get $100. If you spin a 2 or 3, you win $20. If you spin a 4, 5, or 6, you win $5. If you spin anything else, you win nothing. The first thing we want to do is create a probability distribution to represent the game. And just kind of looking ahead, they want the expected value for profit in B. So we want to make sure to factor in this $10 cost to our possible winnings. So I'm going to call this W for my variable. They didn't give us a letter, so you could use something else, and that'd be fine. If I spin a 1, I get $100 minus my 10 that I paid to play. So one possible final value I could have for profit is 90. If I get a 2 or a 3, I win $20, which means my profit after I subtract the $10 would be 10. With a 4, 5, or 6, I win $5, which actually 5 minus the 10 means I would lose $5. And then if I spend anything else, I win nothing. Well, 0 minus 10 means my last profit would be negative $10. Then when it comes to probabilities, I'm spinning the numbers 1 through 10. And the only way I can win that $100 or have a profit of 90 is with 1. So there's a 1/10 probability there. If you want to use the decimal of 0.1, you could. To get $10 would be a 2 or a 3, so that's 2/10. Or you could do 0.2. 4, 5, or 6 is 3 combinations out of 10. That would get me negative 5. And everything else would be 4 of the 10. I haven't talked about where we haven't covered the numbers 7, 8, 9, or 10. And again, you don't need both. I'm just writing both the decimal and the fraction version for the purpose of this. So B says, find the expected value for profit when playing the game and interpret its meaning in the context of the situation. So as far as the value, it would be mu of W, since I use W as my variable. I'm going to write my formula. And that value, if you crunch that out in your calculator, ends up being 5.5. So then as far as the interpretation, over the course of playing this game many times, we expect a profit of $5.50 on average per game. Then part C says, is this a fair game? Well, to be a fair game, we need an expected profit of 0. So no, because the expected value for profit is not 0. Number 3, let the random variable x represent the profit made on a randomly selected day by a certain store. Assume x is approximately normal with a mean of $360 and a standard deviation of 50. So this is really just some good old standard z-score work. For A, my z would be 400 minus 360 divided by my standard deviation of 50, which would be 0.8. My probability statement would be the probability that z is greater than 0.8. And then if we look it up and do our 1 minus, since this is a greater than problem, we would end up with 0.2119. For B, again, I have my z-score. It would be 250 minus my mean, divide by my standard deviation. That gives me a z of negative 2.2. My probability is z less than or equal to match their symbols, of negative 2.2. And I end up with a decimal of 0.0139. This time I don't have to do any subtracting. So that was A, there's B. For C, I need two z-scores. I need the z for 200, which ends up being negative 3.2. I also need the z for 375, which ends up being 0.3. And then my probability statement less than or equal to match their symbol, z, but less than 0.3. And my final probability after I look them both up, then take bigger decimal minus smaller decimal, is 0.617. Number 4, let the random variable x represent the profit made on a randomly selected day by the store stat depot. Assume x is approximately normally distributed with a mean of 360 and a standard deviation of 50. Let y represent the amount of money made by the competitor store StatVantage. Assume that y is approximately normally distributed with a mean of 430 and a standard deviation of 60. So then they want us to find the mean and standard deviation for the total sales of the combined stores on a day where store X's sales are tripled and store Y's sales are doubled from what they normally are. So this is just multiplying by a constant of 3 and multiplying by a constant of 2. And we are just looking for the mean and the standard deviation. So I want mu for tripling X plus doubling Y. And the mean is nice. So I can take 3 times my mean for X plus 2 times my mean for Y. And that will give me my new mean for the random variable, which would be 1940. Then for standard deviation of 3x plus 2y, need to be a little bit more careful. I can take the old standard deviation, which was 50, and I can multiply that safely by the constant. That'll give me my new standard deviation for 3x. I can also take my standard deviation for y and multiply that by the constant. So now I have my two new standard deviations, but that's only for 3x and for 2y, so I need to combine them together. So to do that, I need to make sure I square that whole value that I just figured out. Now they would be variances. Now I can add the variances, but at the end I want a standard deviation, so then we have to do our familiar square rooting after that. And we end up with a standard deviation of 192.09. In B, we now want to find the mean and standard deviation for 1/2 y minus x. So if we're going to do that, again, I want the mean of 1/2 y minus 1/4 x. So be careful. Notice that we have y first this time. So with the mean, I'm going to take 1/2 times the mean for y minus 1/4 times the mean for x. And if we end up multiplying and subtracting those, again, the mean is nice. We end up with a value of 125. For my standard deviation, again, we can take the old standard deviation, which was 60, and multiply by that constant. That'll give me the new standard deviation for 1/2 y. And I can take my old standard deviation for x and multiply by 1/4. That'll give me my new standard deviation for 1/4 x. If we're subtracting the random variables, we still need to add variances. So I need to square both of these so they are variances. And even though we're subtracting the random variables, that variance and that standard deviation get larger. So we add the variances, I square root so that I have a standard deviation at the end, and my standard deviation is 32.5. All right, number 5, the MP3 music files on Sharon's computer have a mean size of 4.0 megabytes and a standard deviation of 1.8 megabytes and are approximately normally distributed. She wants to create a mix of 5 randomly selected songs for a friend, but actually first they just want to know what's the probability that a single song is larger than 5. So this is a standard z-score problem. My mean is 4, so I want to take 5 minus 4 divided by my standard deviation, and I end up with a z of 0.56. And this is a greater than problem because I want to know if it's longer than 5. Or it's not longer, larger than 5. So if you look at 0.56, you end up with 0.7123, but we need to do 1 minus since it's a greater than problem. So 0.2877. Now we get into combining these 5 songs. And in this case, so if M is my variable for her music, in this problem, 5 combined songs would really be M plus M plus M plus M plus M. And that mean would be our old mean, which was 4, and added together 5 times. And certainly you could just do 5 times 4, too, to compute it. Either way, we end up with 20. My new standard deviation I can't just add standard deviation, so I need to take the old standard deviation, square it, and then add that together 5 times. Or you could multiply times 5. I'm just doing this as one last visual reminder that we're really adding the variance together 5 times, and then square rooting to get our new standard deviation. So our new standard deviation is 4.02. So now B was what asked us for the mean. C was that new standard deviation. Now we're ready to tackle D. What is the probability that the mix of 5 songs is larger than 25 megabytes? Well, now I have the mean and standard deviation I need. So now this is just a z-score problem. My x is the 25 megabytes minus my mean divided by my standard deviation. We end up with a z of 1.24. My probability statement, if you're going to do it with letters, you actually would have to say the probability that M plus M plus M plus M plus M is greater than 25. Otherwise, you can just do the normal, like I tend to do, and just do the z greater than our z-score, 1.24. Either way, you end up with 1 minus 0.8925. Because it's a greater than problem, we have to do the 1 minus. So our final answer either way is 0.1075. And again, either one of those symbols will work. You need to do the probability statement with the variables in the problem or just use the z-score version. All right, our last problem is about bowling. Mr. Loss and Mr. Cull bowl every Tuesday night. Over the past few years, Mr. Loss's scores have been approximately normally distributed with a mean of 212 and a standard deviation of 31. During the same period, Mr. Cull's scores have also been approximately normally distributed with a mean of 230 and a standard deviation of 40. Assuming their scores are independent, what is the probability their combined score is more than 500? So if I want their combined score, I really want the mean of L plus C, which I can get by taking the old mean for Mr. Loss and the old mean for Mr. Cull, 230, and adding them together to get 442. My new standard deviation for L plus C, I need to take my old standard deviation and square it so it's a variance, my other old standard deviation and square it so that it is a variance, and then I can add them together safely and square root to get my new standard deviation of 50.61. and then I'm headed to Z-town. Z is 500 minus my mean divided by my standard deviation. And for that, I end up with a z-score of 1.15. The probability that z is greater than 1.15 ends up being 0.1251 after you do your 1 minus the decimal you get from the table. And our last problem, what is the probability that Mr. Loss scores higher than Mr. Cull? So we've tackled this one a couple times, so hopefully you're just doing one last kind of dress rehearsal on this. But in order to tackle this problem, we need to change it a little bit. This is two different distributions. I need to combine them so I can get a single mean and standard deviation. So we're just going to subtract c from both sides of that inequality. So we're really going to find the probability that L minus C is greater than 0. And the reason we can do that now is we can find the mean for L minus C. We know how to do that with our random variables. I would just take the mean of L, which is 212, subtract the mean for Mr. Cull, which is 230, and I get a mean of negative 18. To get the new standard deviation, even though we're subtracting random variables, we still add variances. So we are going to see a familiar value. Take the standard deviation and square it. Take the other standard deviation and square it. Now I can add them together. And I can also square root them to get a new standard deviation of 50.61. And now I'm ready to do my z-score work. The other thing you need to be careful to remember is my x is this 0 that we created. That's what I need to plug in for a z-score. It's 0 minus my mean, which is negative 18. So we really end up with 0 plus 18 over 50.61. I end up with a z-score of 0.36. Be careful, that's not your probability, that's our z-score. So I still need to find the probability that z is greater than 0.36. And after we look up our 0.36 as a z-score and do 1 minus the decimal we get, we end up with 0.3594 as our final answer.